Good afternoon, everyone. My name is Michał Żeliński, and I will be your host during the rest part of the day. Our next session is focused on time series forecasting and whether this well-established domain may benefit from generative AI models. It will be delivered by Jakub Adamczyk, data science engineer at Placewise. So, Jakub, the floor is yours.
Thank you. So I'm Jakub Adamczyk. I'm a data science engineer at Placewise. I'm also a PhD candidate at AGH University of Krakow. And in this presentation, I want to tell you about time series forecasting and whether we can do it with generative AI models, how we can do it, and whether it's worth it. So let's get started. We will start with a short introduction to time series forecasting, just to recap a few things. So in time series forecasting, we have a series of values ordered in time. This time ordering is a crucial part because without it, we would generally just have a typical regression. So in practice, we have discrete time, like for example, separate days or months or years, and we have discrete measurements in those units, and we have continuous values. So for example, sales values or network traffic or inflation per month or any other continuous real value. So we know historical values, right? We have the past data, like in all machine learning, and we want to forecast future values. So we want to predict the values that go further in time. And just like on this image here on the right, we have the past training data and future test data. Of course, when we do train test split in time series, we also take the past data as training and future data as testing. So in time series, as is in the example here, we can have a univariate time series, where we have just one time series ordered in time, just a series of values, or we can have multivariate time series where we have multiple time series together and we want to forecast each and every one of them. Like for example, when we have multiple store locations and we want to forecast sales for all locations, for all stores, we can treat them as multivariate time series. And we can also have auxiliary features, also called exogenous variables, which are just additional features, like for example, is there a promotion, or is it a week before Black Friday, or maybe some information about promotions. So any other feature engineering that we can do for time series, right? But in the most basic case, we just have a series of values ordered in time, single variate, and we need to forecast it to predict the future values. And forecasting applications are basically everywhere. Those are just general, most famous examples on the slide. For example, in business, we want to forecast production, sales, demand, very obvious things based on the historical data. And we also have, for example, predictive maintenance, very interesting area where we predict the lifetime of some parts, whether we should stop a machine and fix it or change some parts based on time series forecasting. So in economics and econometrics, we have a lot of applications, like we want to forecast GDP, inflation, energy prices or production or other macroeconomic values, or we can forecast stock values, options pricing, and there are a lot of companies that basically their whole business model is forecasting time series for finance, right? And we have weather forecasting, the forecasting that we all use. We forecast temperature, pressure, air quality, anything related to the air. And in cloud, in DevOps, we forecast, for example, network traffic. We can forecast the number of requests per second based on historical data. And we can use it in machine learning to do so-called predictive VM scaling. This is offered by all major cloud providers, where you want to scale up or down your number of virtual machines based on the machine learning forecasts of your traffic. So it will be quite intelligent scaling up and down. So we have a lot of different applications. They are more or less automated, different resolution, different amount of data, of course. But we need to forecast them all. And traditionally, we applied some very traditional statistical methods for forecasting, and we'll talk a bit about those. And in forecasting, we basically have a regression task, right? Because we know past values. And of course, in training data, we know both training and testing data. I want to forecast or estimate the continuous real values for the unknown future, right? So this is a regression task because we forecast continuous values, but of course with some time-specific additions. So for example, our algorithms have to be aware that some regression values come before or after other values. So it doesn't matter whether those are statistical models, neural networks, or any other type of model. This is basically a regression task. So traditional models are very heavily based in many cases on decomposition of time series into trend, seasonal, and residual components. So if you have original data here on the left, we see that those are definitely some patterns there. And the overall long-term trend of the time series is whether it's going upwards or downwards. So you can see it here on the upper right side. So the trend generally tells you whether the time series is going upwards or downwards. Some series show clear trends, others don't. We can, of course, also have seasonal components where we have periodic repeatable changes with some given period. For example, when you have store closed on Sundays, every week we have 0 sales on Sundays, right? So this is weekly seasonality. Or for example, every year before Black Friday, we have higher sales. So this is yearly seasonality, right? We can have many seasonalities. And we, of course, have residual with any other changes or shocks. So statistical methods are very heavily assume that this decomposition can be done. And in many cases, they have strong assumptions like one seasonality, non-changing seasonality. Neural models have less of those assumptions, but they still do assume some of those things. So if this decomposition cannot be done, or it's very hard, or doesn't fit into your time series, the traditional models will struggle. And many of the traditional methods also assume the stationary time series, so that the one that has no trend. Here on the upper side, we see a time series with clear trend. So this is a non-stationary time series, and they apply differencing, so they change values of time series into changes or deltas between time steps. So instead of, for example, a stock value here on the upper side, we can have the change in stock value between different days. So this is the first differencing here, or we can difference many times, right? And getting a stationary time series is often very difficult or even impossible in some cases. So also, if you cannot fill this assumption, the traditional methods may struggle a lot. So we have a lot of traditional models with very different assumptions, different computational costs. So we can use them in different situations. We have a lot of random walk-based models. We have exponential smoothing, or ETS. For example, famous Holt-Winters model. We have the whole ARIMA family with SARIMA, ARIMAX, etc. We have newer statistical models like BATS, TBATS, or Theta. We have very famous financial ones like ARCH, GARCH. Many regression-based. We have Prophet model. So a lot of models. Those are, of course, not all of them, and a lot to choose from. And each and every one of them has different hyperparameters, different methods for tuning them. Maybe they are not even implemented in Python. So traditional forecasting has a few problems, as you can see. So firstly, we have a lot of models to choose from, and it's very hard in many cases to know a priori which model to choose, and checking many models is, of course, computationally expensive. And you need to do feature engineering in many cases for them to perform really well. And feature engineering is often non-obvious. For example, it requires deep domain knowledge, for example, in finance, and in a lot of cases, to get appropriate features, formulas, understand what data you can and cannot get easily. So feature engineering is also something that you have to do. Hyperparameter optimization is, of course, can be automated, but it has certain costs, especially if you have long time series, if you want to tune very carefully, or if your model is unstable, like many neural networks. And those models make a lot of assumptions. You have to check those assumptions, perform error analysis for those models to perform really well. So they cannot be automated that easily, or at least this automation comes with a high cost. And of course, there's no transfer learning in those traditional methods. Many neural networks, many neural models also do not use transfer learning in this traditional forecasting approach. So in no transfer learning, it's in many cases pretty inconvenient, because, for example, you have a lot of stores, you have historical data, and you have a new store. So you should reasonably be able to do transfer learning, right, based on the data that you have, and you cannot do this with this traditional approaches. So those problems have a few consequences in practice. They have computational cost, because you have to choose typically many models, tune them all. It's hard to automate in some cases, especially if you care about checking those assumptions, about error analysis, and it can be hard to scale, particularly if you require high degree of automation, like, for example, in predictive VM scaling or predictive maintenance, where we have many different models, many different time series. We need to scale a lot. They are very different from each other. So in those cases, we care about automating highly and scaling a lot. So we need something to solve those problems. And here, fortunately, we have the whole GPT revolution, right? We have generative AI foundation models. So let's talk a bit about that, because people, of course, also wanted to apply this to time series forecasting. And GPT models, this probably will be familiar to you. The generative pre-training approach, the GPT, is a decoder-only model. right? And in decoder-only models, as our inputs, we use token embeddings. So we take some tokens, like for example, parts of words, and we tokenize those words into tokens. Each token is represented as an embedding, and our model outputs or generates tokens, the most probable next token based on the previous tokens. So because we do attention only with previous tokens, right? This is also called causal attention. So in GPT model, if you have a word a long time ago, the next word will attend only to those previous words. And it will, based on the a long time ago tokens, it will generate one next token. And then you input this new token, generated token, into your prompt or your previous text, and you generate further, right? This is the standard GPT approach. In pre-training, this is particularly convenient because you just use previous tokens to generate next most probable token, and you minimize loss on those generated tokens. So you want to generate the most probable things, and you want those probabilities to be close to reality, to your training data. So pre-training GPT models is pretty convenient. In the token generation, as I said before, you have input, you generate one next token, you put this token into your training data, and you generate next token, the next most probable token. And right now, we start to see some similarities to time series, right? Because we have past data, and we generate next token. We generate the most probable values. We attend only to the past. The GPT models have some notion of order, the previous and next tokens, past and the future. They generate new values for the future. They use new data to input it into historical data. So this comes pretty natural to time series, this generative approach, actually. So why GPT models for time series? Apart from this very natural analogy, they have a few advantages. Firstly, they pre-train very effectively. So they have surprisingly good transfer learning capabilities. They can even transfer to tasks that they have not been explicitly trained to. And pre-training is very, very hard for time series. For many years, and people have said that pre-training for time series is impossible or too hard, and many say this even now. And it turns out that GPT models, due to this easy pre-training, fit really well into time series because they ease this problem. And they also show the emergent abilities on some scale. If you have extremely large foundation models, they show these abilities that they can do things that they were not trained to do. Like, for example, in context learning, where you provide a few shot prompting to your model. Those models have never been trained to do this, but they actually can improve the results with few shot prompting. Or they can do zero-shot learning, where for example, ChatGPT has never been programmed to be a Python programmer, right? It was never trained on Python programming, but it can do it. It's just an emergent ability due to this enormous amount of data and huge model that can save those abilities in the weights. So those emergent abilities can transfer to time series, understand from the context of time series, from historical data, the new patterns in your new data set. And we have massive data and compute available. This has, for a long time, been a huge limitation for time series. We did not have any large pre-training data sets, or even generally not much data for time series. But right now, we have a lot of data for time series, a lot of network traffic data sets, a lot of commercial data sets publicly available for use. And we also have a huge number of GPUs that we can use. And combining all of those things together, the effective pre-training, the emergent abilities, they say that this should work. Massive data and compute enable us to do this. And thanks to this, we can use this generative AI approach for time series. And foundation models, based on the Wikipedia definition, they are models that are trained on broad data, such that those models can be applied across a wide range of use cases. So foundation models can be a domain expert. So for example, foundation model can be a general expert in time series forecasting. And the size here matters. You need large models, massive data sets, and a lot of compute. So all those things together come into the foundation model. Foundation models are surprisingly simple in many cases. So the GPT model is really not complicated, right? They just scale it up really well. But the model is simple. They rely on the data itself to provide the abilities into the model. So we need a lot of data, right? It's based on the representation learning paradigm, where the model should encode the general purpose knowledge into itself. The weights of the model should encode the general knowledge of the domain, and we want to pre-train the domain expert, which can perform well on new tasks in this domain. And forecasting can be thought, as I said before, as generative task, and we can use and train those foundation models for forecasting, because we want to generate future values, right? We have the past values, we want to generate next ones based on the context, on the historical data. So this is basically a prompt completion. You have a prompt, your historical data, you want to generate next tokens in your generative approach. So this is exactly what GPT model will do. Of course, we have some problems to solve, and this is why it took so many years to do this, because we need to tokenize our inputs somehow, which is very non-trivial for time series. We have to understand what tokens should we generate, how should we generate those values, and where to take the pre-training data from. And all of those things have been solved to some degree, at least, in time series forecast foundation models, and they share some common features between them. Firstly, they are all transformers. This is not surprising, right? They have quite simple architectures because they borrow from transformers again. They use tokenization. Also, tokenization is called patching in time series. This is one and the same. Tokenization and patching, just the same thing. They also are pre-trained on massive datasets, but they are also varied. So they are not only in encoder they are not only decoder only models like GPT approach, but they are also encoder only like BERT, and they are also encoder decoder like the transformer for translations. They can be for univariate or multivariate time series forecasting, and they also can or may not have exogenous variable support. So we have GPT-like, BERT-like, transformer-like, multivariate models, so a lot to choose from. Here in this presentation, I will focus on the decoder-only models because I think they are very natural for time series, and I think they are particularly interesting. So the idea is to rely on massive and varied data rather than complicated models. Those variations are relatively small. And the interesting, fascinating thing about those models is that they can perform zero-shot forecasting. So they can predict new time series. They can forecast for new time series without any training for this time series. So you just input new time series, tell the model, okay, perform inference, and they just generate forecast, even if they see this time series for the first time. This is a new emergent ability of large time series models. So those models are relatively new. So the first time series foundation model arguably is the time GPT model from Nixla in 2023. It's not open source, but the white paper says that this is an encoder-decoder architecture, interestingly. And further models are LagLama and TimesFM, which applied the decoder approach. They are fully open source, so we will focus on them. Particularly, we will focus on TimesFM because I think it's pretty simple, the simplest arguably of those all models, and it is a decoder-only model for time series forecasting specifically. We also have Chronos from Amazon. We have Moira and Moment, encoder-only models. The last one is basically the only one here made only by scientists. So the companies also make a lot of models because they have really a lot of interest in this, because companies need to forecast time series. So they make those models and make them publicly available to also, of course, make them more known. So we'll focus on TimesFM here, and TimesFM will be just the GPT architecture, but for time series. So the idea is to tokenize time series somehow, to generate tokens with those continuous values, right? So generate those real values and apply GPT architecture inside it. So we take time series, tokenize it, just the GPT architecture with very slight changes, and we output the values. So in TimesFM, I will not focus on the inside of this network because it's just the GPT architecture with very small changes. You can read the paper, but they're very, very small. The interesting parts are the inputs and outputs. So in terms of pre-training, because this was one of the things that enabled this approach, the key to success was really using a massive data here, a lot of real-world data and varied data. So we had Wikipedia traffic, Google Trends traffic, M4 forecasting from sales, and many different data sets. So a lot of varied real-world data. And in addition, they used synthetic data. So they generated data to show different time series to the model. So they generated trends, seasonalities, random walks, ARIMA processes. In time series, we can generate many different time series, and we know that they are quite realistic. So we can generate them well. There's no problem with generation because those are not generative models. They are just mathematical functions to generate things. So they work really well. This is unfortunately a closed source data set, but all of those partial data sets, they are publicly available, so you can use them. But this was really a massive data set, and this was the first element here. The second element was tokenization. So it's also known as patching because it was proposed by patch TST model and subsequently is used by many other models. So the patch is a continuous series of values, just like very similar to token in NLP, but in NLP we have discrete tokens, right? We have, for example, a few letters forming a token. Here you take next values of time series, for example 16, and this continuous 16 values creates a one token from real values for that is input to the transformer layers, and they are typically similar to convolutional filters, so that we have stride lower than patch, so they will be overlapping. This reduces overfitting a bit. And using patches or tokens instead of raw time series values, firstly, lowers complexity a lot, because we remember that attention is quadratic in complexity. And here, if we use tokenization, this is quadratic in number of tokens instead of raw time series values. And this enables you longer look back. You can look into long past, which is pretty useful in practice. So you just basically take next windows of values, input this into your transformer, very simple scheme of tokenization, and it works really well. In terms of output tokens, remember that GPT generates only one token at a time. So here we use the approach where one output token is one patch. So we output, for example, 128 values at a time. So we output a lot of values at a time to avoid compounding errors over time. If you use, for example, ARIMA model, it compounds a lot of errors due to this autoregressive approach where you input your forecast into your training data. Here, we output many values to avoid this. This is called autoregressive forecasting, where this is also used when you need long horizons. So if, for example, if you want to forecast 1,000 steps into the future, you predict 128 values, add them into your context, into your prompt, your training data, and you forecast further. This is just like GPT works. If you use ChatGPT, for example, it has a text, it has this context, generates one token, adds this token to its input, and predicts further, right? So this is exactly the same, but for time series. And those big patches help reduce compounding errors if you have long horizons, because in many cases, you just need less than 128, and this can also be longer. So in benchmarks in the paper, they evaluated only zero-shot forecasting. So they did not train this model at all. And it turns out that on those 3 different benchmarks, the model was either the best or very close to the best. But remember that, for example, in this middle benchmark, the best model was ARIMA. It took a lot of time to train for each and every data set, to train, tune, etc. And this TimesFM, it was only inference. There was no training at all. Similarly here, it was not the best in this benchmark, but it was close to the best with no training at all. So this is the power of generative AI in time series forecasting. They can forecast without any training. This is really useful in practice. And this practice, because I implemented the business intelligence forecasting. So in Placewise, we had the API for clients, so-called data API, where they can ask the historical data from them for any data segment. For example, they can get time series for any given KPI, like, for example, give me sales among young people, or give me the number of used promotional coupons among women, or any other data segment. So the client can ask the BI system for any segment of data. We do not know beforehand which data they will ask for. And there are infinitely many combinations here, basically. And in forecasting API, the client can send this time series and the horizon they want, and they want the predicted values for time series. So we do not know the time series beforehand. We cannot train models before the client's request. So the client will need the forecast for his unique time series at the time of request. So training and tuning and etc. many models is not feasible simply. So if you use TimesFM, we can just have a single model that will handle all clients without any training at all. So we just create an instance of TimesFM, input this new time series from a client upon request, and we just forecast it with zero-shot forecasting. So no tuning is required. It's very simple, very fast, works for any data out of the box. Scaling those microservice approaches is very trivial because we just spawn new instances. You can download TimesFM from Hugging Face and it will just work. So it's very, very useful in this use case. disadvantages of this approach, because of course there are some. So firstly, those results will not be typically the best. You can get better results than this zero-shot forecasting, but it depends on your use case. Maybe those results are just good enough. In most use cases commercially that I have found, just good enough model is well deployed to production. The bigger disadvantage is that it requires much more resources than traditional methods. So in traditional methods for forecasting, this is basically a linear regression. You can run this on anything. But here, you need at least 2 to 3 gigabytes of RAM, a few CPU cores. So this has some cost, right? Because this is a neural network. After all, it won't run itself. And when you create an instance of a model, you need to tell it what will be the direct horizon for forecasting. So whether it will be 128 values into the future, maybe shorter, maybe longer. But remember that longer horizon, well, it requires more compute because it's more values to forecast. So longer forecasts will always be autoregressive, but shorter forecasts, well, you don't want too long horizons due to this computational cost. So you have to balance this. You have this trade-off, what the clients will typically need in terms of horizon, because you don't want to overshoot due to cost. And it depends. Those are not huge disadvantages, of course, but they are here, so you have to consider them. And other LLMs for time series, I think that 2 LLMs are pretty interesting. In particular, I think the first one is Moment. Moment is a BERT-like model, encoder only, where they were trained on time series reconstruction. So just like BERT, just like language modeling, but for time series, and it's multitask. It's not only for forecasting. Moment is also for time series classification, anomaly detection, imputation of missing values. So you can do many things with Moment. If you need something other than time series forecasting, this may be a good choice. And it was pre-trained on a huge data set called time series pile, and it was made publicly available. So if you want to experiment, train something by yourself, or maybe just use this partially, some subdomain of this data set, you can take it and just use it. So I think the Moment family of models is pretty interesting, also pretty simple because it's just BERT, but for time series. And the second model is LagLlama. It's GPT-like, it's decoder only, but LagLlama is probabilistic. So it uses the Llama model. It uses the Llama model inside, but as the head of the model, the so-called distribution head, it forecasts not only a single value, it forecasts the whole distribution. So it gives you confidence intervals. If you don't need only the point forecast, the one value, but you also need the confidence intervals, like for example, for 90% probability, the value will be between this and this, the LagLlama will be a good choice because it turns out that it's really good for probabilistic forecasts. It uses not only raw time series tokens, but also lagged features, so like moving averages or sums or other features that helps it understand this historical context. So just to recap, TimesFM for point forecasts, Moment really good for many different tasks, and LagLlama for probabilistic forecasts. So this is all in this presentation. Thank you for watching. I hope you liked it. I hope you learned something. I hope that generative AI for time series is an interesting approach and you may use it. Of course, please ask questions, rate the presentation, and thank you for your attention.
Thank you, Jakub, for the very interesting presentation. I don't see any questions remaining in the chat window, so I think that would be it. Thanks so much, everybody, and see you in 5 minutes, or actually 10 minutes, with the next block.